This conference will now be recorded.
We'll give it just another minute or two, Haley, just so anyone last minute or running a minute behind or something can hear all the details.
Okay. Sounds good.
Hey. Okay. All right. We'll go ahead and get started. Hello, everyone. Thank you for joining us for our second to last brown bag of the season this year. Today, we're going to be talking about protecting our waters. This is Haley. Kujawa is working on a project that will help us predict climate and land use changes and how those will impact our watershed moving forward. Haley is our Margaret A. Davidson Fellow, which is a national program through the National Oceanic and Atmospheric Administration. It's Friday, my brain just quit on me, sorry. And every National Estuarine Research Reserve in the system was awarded a Davidson Fellow, and we were lucky enough to get Haley. And she is going to introduce her project. She'll be working with us for another year. She just wrapped up her first year with us. We got to see her in person once, but she'll be up in a couple weeks as well, and she'll let you know all about that. So Haley, take it away. If people can keep muted and keep their cameras off, that's great. If you have questions, please put them in the chat. And Haley, We'll answer them along the way. And just as an FYI, this is being recorded, and hopefully we'll be able to put it on our YouTube playlist. So if you don't catch everything, or if anyone needs to see it again, it will be up and available. All right, Haley.
Okay, thanks everyone for coming. I really appreciate it. And I'm just gonna get right into it. So, okay. Picture yourself a citizen of Toledo, Ohio on August 2nd, 2014. Here you are waiting in long lines to access potable water for your home. A do not drink advisory has been issued on the water supply. The concentration of microcystin, a liver toxin produced by the algal bloom in Lake Erie, is too high in the drinking water plant and poses a serious risk to public health. Boiling the water will simply not remove the toxin. There's high uncertainty as to when the water will be safe to drink again, with no apparent end in sight. Fortunately, the drinking water plant was able to adapt within 3 days' time, and the advisory was lifted. However, harmful algal blooms in Lake Erie are projected to worsen with climate change, and all of us in the Lake Erie Basin need to be better prepared to manage bloom in the future to avoid similar public health crises. Hi, I'm Haley. I build watershed models that inform management. Today, I'm hoping you'll understand the usefulness of watershed models and as a tool in the decision-making process for harmful algal blooms. I'm going to dive in a bit on how watershed models can be specifically address nutrient management in the Lake Erie region. Then we'll talk a bit about the specifics on the watershed model I'm building for Old Woman Creek. Watershed models can be used to inform watershed and coastal management. So to talk a bit about harmful algal blooms and what they are, harmful algal blooms occur when excess nutrients leave in the runoff of agricultural and urban areas. High nutrient availability in the downstream waterway allows for algal blooms to thrive. Blooms can be toxic and affect drinking water, swimming and recreation, tourism, the fishing industry, and ecology. The best way to manage these blooms is to intercept nutrients from agricultural and urban runoff before it enters into the downstream waterways. For the next few slides, I'm specifically going to be talking about phosphorus, as it's the limiting nutrient in freshwater blooms and a priority for management. Sources of phosphorus from municipal systems such as in-yard fertilizer, from wastewater treatment plants, phosphorus in soaps have been drastically reduced through legislation and through improved nutrient removal technologies. Significant improvements in these types of nutrient pollution, also known as point source pollution, have been recognized since the 1980s. However, despite decreases in phosphorus loading from municipal systems, in many watersheds, phosphorus loading has been increasing. On the left is a graph of soluble reactive phosphorus increasing since the 1970s in the Sandusky River, a tributary to the Western Lake Erie Basin. Using nutrient balance methods, we can see non-point source comprises the majority of soluble reactive phosphorus load in the Western Basin. This is important to know because the Western Basin is highly agricultural and a majority of the non-point source is from farm operations. So if we can target these farm operations with management practices to reduce nutrients, we could help reduce phosphorus loading. So the good news, non-point source pollution can be reduced through improved management of nutrients on farms and implementing additional ecological conservation strategies that use physical means to capture nutrients. In this example on the left, livestock are left to wander freely in the stream, creating no buffer between the stream and farm, allowing for large quantities of nutrients from livestock to be released downstream and enter Lake Erie. However, on the right, the cows have been removed from the stream, a grass buffer has been placed around the stream, and the grass buffer intercepts some of the phosphorus before it gets into the waterway and leaves downstream to go to Lake Erie. In this scenario, a much lower quantity of phosphorus is delivered to Lake Erie and can help restrict the growth of harmful algal blooms by limiting nutrients. Some of the practices that are used in conservation, I'm going to walk you through a few. They're very varied and there's a lot, but one of them is conservation tillage. This is where you either use no-till to help improve soil health, which in turn can help retain water and lower the quantities of nutrients that's delivered downstream. Another practice is winter cover crops. This is putting a crop during the non-growing season. So when you're not growing corn or soy, you're growing a crop to cover the ground. That way there's less, the ground is less susceptible to nutrient and sediment runoff in the wintertime. Grass waterways can be put in fields to intercept areas of high flows to help slow the flow down, deposit sediments and nutrients, and also protect that ground from erosion. Nutrient management deals with what is called the 4 R's, so the right time, right rate, right place, and right source. So an example of this would not be not putting fertilizer on the field during the winter, especially if nothing is growing, because putting fertilizer on the winter when ground is maybe frozen and there's nothing growing leaves nutrients really susceptible to runoff. Another practice is vegetated filter strips, similar to the grass waterways, where water runs over this filter strip. It helps to slow the flow, deposit sediments and nutrients, and filter out some of those water quality issues. And then wetlands, similarly, can be put on farms to intercept runoff and help deposit phosphorus and sediment in them, as well as transform nitrogen before it goes downstream. And wetlands also provide a pretty good ecological habitat. So these are a couple practices that could help reduce nutrients from farm fields to downstream to Lake Erie. And how we quantify the effects of these practices is using edge of field data. So in Ohio, we have a very extensive edge of field network run by the USDA. Edge of field studies quantify the amount of nutrient and sediment reduction of best management practices. Excuse me. These studies help to quantify discharge, nutrients, sediment from the surface and subsurface areas and runoff before and after a practice was implemented. These really get at what kinds of reductions in nutrients and sediment can we expect with these practices. However, they're time and money intensive and cannot be extrapolated to large regions. And this is where watershed models can be used to scale up edge of field data to larger regions and generate simulations that are more temporally and spatially comprehensive. So they can cover longer periods of time as well as cover larger areas. The soil and water assessment tool is particularly useful in the Lake Erie region because of its ability to simulate managed lands and agricultural best management practices. The model uses topography, land cover, soil, and weather data to simulate hydrology and the movement of nutrients and sediment. So here's the basic water budget in SWAT, and I'm going to sort of walk you through how the basics of a watershed model work. So the first thing that happens is we force the model with precipitation data. This is usually observed data from a climate station. The precipitation hits the ground, and from there's a lot of different pathways that it could take to leave. So one of those pathways is evapotranspiration, leaving off of plants or off the ground through evaporation. Another pathway is leaving through surface runoff, so hitting the ground and just running off sort of in the sheet flow and then into the stream. In agricultural regions, there are lots of tiles that are used. So these are just pipes put into fields that help drain fields so that fields are not inundated when crops are growing and they won't die. So in agricultural watersheds like Old Woman Creek, there is a good amount of tiling. And in the watershed model, surface runoff can either be generated and leave as surface runoff or tile discharge. And this is where I'm going to talk about the concept of model parameters, which I might mention later. But one thing that watershed modelers do to sort of decide how much water is leaving in the surface runoff versus how much is leaving in the tile is adjust parameters to sort of match what we think is most accurate or representative of reality. So you could change the parameters so that more discharge is leaving through the tiles, or you could alter the parameters so more discharge is leaving through the surface runoff, depending on what you know about the watershed. However, this is usually up to each modeler's Each modeler has to make a decision on what is most representative of the watershed using local expertise, as well as edge of field data. And this is kind of where model uncertainty comes into play, where we're not exactly sure what is the best way to represent the system with the model, but we do the best with the tools we have available. A few other things the soil and water assessment tool does is it does simulate crop growth. So it can simulate, like I said, it's really great for agricultural lands because it simulate corn and soy growth. And also the constituents involved in water quality, such as nitrogen, phosphorus, and sediment, can all be simulated with SWAT, pesticides as well. But nitrogen, phosphorus, and sediment can sometimes be a little bit more difficult to get right than hydrology because there's not only is it just the movement of water we're looking at, but there are transformations happening within the nitrogen and phosphorus cycle. So this is another piece of that model uncertainty where we are trying to capture reality as accurate as possible, but there's a lot going on, especially in complex systems like Old Woman Creek. Now I'm going to switch gears and talk a bit about how the soil and water assessment tool has been used in the Lake Erie region. I'm going to be talking about a previous project in the Maumee River watershed. And this project ran from 2016 to 2019. It's called the Harmful Algal Bloom Research Initiative Multi-Model Project. There were 5 modeling groups involved, so each group built a model. The groups are listed here: Ohio State, University of Michigan, Lemno Tech, Heidelberg, University of Toledo. The multi-model project was used because the multiple models helped improve predictive power, and also using the multiple models helped to capture some of that model uncertainty within each watershed model. So many of you may know about Lake Erie's harmful algal bloom and the associated Great Lake Water Quality Agreement targets. So there are targets that Lake Erie is trying to meet to reduce the extent of the harmful algal bloom. And one way to assess how we can meet those reduction targets is to use a soil and water assessment tool to run agricultural management scenarios where there could be potential phosphorus reduction. So I'm going to orient you to the first portion of this project, was really looking at how can we meet the Lake Erie phosphorus loading targets. First on this graph, we have total phosphorus concentrations on the left right here. On the right, dissolved reactive phosphorus concentrations. Total phosphorus is the blue bars, and dissolved reactive phosphorus is the orange bars. The first scenario here listed is the baseline. So this is business as usual, no changes to agricultural management. This is what we would expect if no changes in agricultural management were made. The next scenario is a scenario we're running 58% cover crops, 50% subsurface placement. I didn't mention this one before, but it's where you place phosphorus or incorporate it within the soil. That way it's less susceptible to runoff. And then the last one was 78% buffer strips. And these were implemented at random wherever across the watershed. The next scenario is that same scenario, but it's targeted to areas of high phosphorus loading. And then this green line here, this is the phosphorus loading targets that we want to reach. So above the line is not meeting the target, and below the line is meeting the target. So the lower the bar is, the better, the more phosphorus reduction we're seeing. And to explain a little bit about how we would read a scenario, you can see some of the scenarios for total phosphorus did on average meet that phosphorus loading target, like this scenario here. I'm not sure if you can see my mouse. In this scenario here, we did find that dissolved reactive phosphorus would be much harder to meet the targets, but we are still seeing reductions relative to the baseline. So even though we're not meeting that target, the models did show that some of the suites of practices that we used were helpful in reducing phosphorus, which is promising. So the multiple models helped capture variability in meeting the water quality goals. So we got a bit of a range and helped to capture some of that uncertainty. And throughout this project, stakeholders were involved to improve scenario development. So they were very involved in what scenarios would be feasible for farmers in this region, what sorts of rates of adoption could we realistically expect. They helped us interpret the scenarios and also helped us with outreach of this project. Okay, the next portion of this project was how well can SWAT predict critical source areas. So when I mentioned in the previous slide, the targeting of practices to areas of high phosphorus loading, critical source areas are subunits of the watershed that contribute disproportionately high loadings, either nutrients or sediment. These can be really useful to know in targeting practices because then you're sort of getting the highest bang for your buck. You'll get the most nutrient loading reductions if you place practices in these regions. However, they're highly uncertain based on what data and what assumptions modelers made in setting up their watershed model. So here you can see we have discharge on the left, dissolved directed phosphorus in the middle, total phosphorus on the right. Yellow is only one model agreed that subunit or sub-watershed was a critical source area, and the dark blue is all 5 models agreed that that area was a critical source area. So what this project found was that critical source area simulations varied substantially across models and could be pretty uncertain. However, some sub-watersheds were identified as critical source areas across all the models, and in this project, those may be prioritized for management because although there's a lot of uncertainty, on the flip side, there was some certainty for some areas. So the last portion of this project was looking at hydrology in a mid-century climate. I'm going to orient you to this graph again. So we have the baseline scenario, which is a business as usual, no changes in management across time. And then we have an increased conservation scenario, which was 60% cover crops, 68% subsurface placement, and 50% buffer strips. We ran 6 climate models through each of the 5 SWAT models. So each of these box plots you're seeing, that's the summary of that ensemble. So 6 climate models through 5 SWAT models, 30 results total. And then on the y-axis here, we have the change from the historical period to the mid-century. And this is as a percentage. So first, we're going to look over here at the hydrology variables. So we have discharge, surface runoff, subsurface discharge or tile drainage, and then evapotranspiration. Between the baseline and increased conservation, we're not really seeing any differences, which makes sense because these practices were mainly meant to target nutrients and don't really retain a lot of water or change the hydrology. So discharge, we're seeing slight increases in discharge, decreases in surface runoff, increases in subsurface discharge, and increases in evapotranspiration. On the flip side, for the nutrients, we have total phosphorus here, dissolved reactive phosphorus, and total nitrogen. Contrary to what we saw with the hydrology variables, we are seeing between the baseline and increased conservation significant reductions with increased conservation and climate, and all of those are significant, statistically significant, as indicated by these stars above each of the plots. So overall, in this portion of the project, we found that multiple watershed models helped provide robust predictions of decreased nutrient loading with increased agricultural conservation in a future climate change. And one other portion of this project was looking at which was the climate model or the SWAT model generating more uncertainty in the predictions, which is important for modelers to know and setting up their projects and accounting for uncertainty. We found discharge and nitrogen prediction uncertainty was largely contributed by the climate model, but on the flip side, phosphorus, the total and dissolved fractions prediction was mainly driven by SWAT. And this is important to know, like I said, when setting up a project and to account for what sorts of error bars do you need to have and how do you need to message uncertainty and results when a project is finalized if you don't have multiple watershed models like we did in this project. And throughout the entirety of that project, stakeholder engagement was a critical component. It led to a lot of projects post this project on working on SWAT improvements so we can better simulate some of the practices of interest. So one of them is improving the simulation of improved soil health in SWAT. SWAT really wasn't able to capture some of the benefits of improving soil health, such as retaining water on fields. So there was a project that came out of that is, I think, wrapping up now and is being improved. But that was through the help of stakeholders identifying that as a gap in SWAT. That project came out of that. And then another project where we looked at drainage water management, which is where you, in the tile drains, you put a structure to retain water on the fields, and through the reductions in flows helps reduce the amount of nutrients delivered downstream. So you can keep the water in the field when crops are growing, and you can release water when there is a big storm or when the field needs to be drained for management or for equipment to go on the field. And we weren't sure about SWAT's ability to simulate drainage water management very accurately. So there's currently a project going on where we're using edge of field data where drainage water management is being implemented and comparing it to the SWAT model and seeing how well are we capturing drainage water management and what changes do we need to make in the model to be able to capture this accurately. Okay. Now I'm going to switch gears a bit and talk about the project that I'm doing here at Old Woman Creek, building a soil and water assessment tool, and I might refer to it as Old Woman Creek SWAT Plus. Okay. The goal for this model, different from the previous project, which was to use multiple models to capture uncertainty and improve prediction. In this project, the main goal really is to create a soil and water assessment tool that incorporates both the watershed and the estuary so that we are able to run scenarios and see the vulnerabilities of the whole system to climate and land use change. I'm going to loop back to talking about incorporation of the estuary, but just wanted you to keep in mind that the end goal of this project is to create this tool that can support coastal and watershed management decisions. So the first portion to building a soil and water assessment tool is to collect some data. There's a few basic data layers that go into the model, such as the soils data. You can get this from the Surgo data set, elevation data from USGS, and then land use data from USDA. These all get overlaid on top of each other. And then using delineation thresholds that I defined, we have our breakup of the watershed model. So here is the Old Woman Creek watershed delineation. These are the subbasins, so they're kind of next to the whole watershed. These are the second, sorry, I saw the chat bubble. These are the second largest units in the model. The entire model the watershed was delineated to about 71 kilometers squared, and we have about 40 total subbasins. The next unit, the next largest unit is the landscape units, and this is actually a new development in the SWAT Plus model, which is a recent update to the SWAT model. These help define differently the floodplain areas, which are more wet and inundated. So think like a river area or a wetland versus maybe something that's more upslope and is more dry, which is important for separating different processes that happen in these areas because you can imagine that a dry field versus a wet stream, there's a lot of different nutrient processing that's going to happen between those two areas. So in SWAT Plus, we now have the separation of those two. And the smallest unit is the hydrologic response unit. And here you can see I've zoomed in here on some of the HRUs. So these are areas that lump similar land use, soils, and slopes. And they're again based on user-defined thresholds. But this is the smallest unit where everything is being modeled, and then we're lumping it to the landscape units, then to the subbasin, and then getting outputs for the entire watershed.
Hey, Haley. We had a question come in, so we'll jump back a little bit. It's a question about the buffers. What happens to the nutrients in a buffer? And does the buffer eventually get filled with nutrients, thus limiting its impact? You can read it in the chat if that would help you.
Yeah, that's a great question. I think okay, oh, I can read it in the chat. Yeah, let me open the chat real quick. Nutrients in the buffer. Yeah, so some of the nutrients can be uptaken by the grass that's growing. I don't know anything about the buffer eventually getting filled. Maybe with sediment, that might be an issue, which would then maybe affect the effectiveness of the buffer, but I can't, off the top of my head, think about like buffer maintenance, but I think that is a thing. Yeah, so I think over time, all of the management practices need some sort of maintenance, and I'm not sure about the lifetime of them at the moment, but yeah, that could be a potential issue. I'm not sure how that's represented in the model right now, but it would be interesting to look into. I hope that answered your question, but we can loop back to it at the end if you want to talk about it. Okay, so I'll keep going real quick. And for the Old Woman Creek Watershed model, here is the land use that we put into the model. So a little over 25% of it is forested, less than 10% of it is urban, most of the watershed is corn and soybean rotations, and then there's about 10% as pasture. And I'm going to talk a little bit about some of the management and the practices that I edited into the model, into the management that's specific to Old Woman Creek. So one of them being tile drainage. Again, these are the pipes put into the fields to help drain fields. About 67% of the watershed area has tile drainage now. Split nitrogen applications. This is where instead of applying nitrogen all at once at the beginning of the season, you apply it at 2 different points in the season. That way, crops have a better opportunity to uptake it when they need it, and less of it is susceptible to runoff. About 53% of cropland acres have that practice on it. Cover crops, about 10% of cropland acres have that practice on it right now. And no-till is about 25% in the watershed. So the next step, as I mentioned before, is to force the model with 10 years of observed climate data. You don't have to do 10 years, but I chose 10 years for the Old Woman Creek swat model. So we're using data at the Old Woman Creek Meteorological Station. And here you can see the orange bars represent the total precipitation for each year, and then the blue line is the average temperature. So the years that we're using, we're capturing a good variability in the climate, which is great because we want to ensure that the model can capture extreme years of wetness and years of drought if we're going to want to run climate scenarios into the future. So 2012 was a really dry year. It was a drought year versus 2019 was a pretty wet year, and 2017. So we're capturing a lot of that climate variability, ensuring that the model can perform well when given those inputs. And then once the model is built, this is just an example data set to show you the practice of calibration and validation, but this is how we check that the uncertainty from the watershed model is within a range that is not completely misrepresenting the watershed. So through this technique, we use observed data, time series of observed data. We compare our simulated data to it, and then we are able to tweak parameters during the calibration period to get a good fit. And we have hydrologic statistics that can help ensure that we do have a good fit. We also use visual tools to see that. And then in the validation period, we're no longer tweaking parameters. We're just checking, does this still hold up against this other time series? So this helps ensure that we have an accurate representation of the watershed. And you can look at variables such as flow, total phosphorus, dissolved reactive phosphorus, sediment, and ensure that all of these outputs are looking good. So in the Oldham Creek watershed model, I'm really interested in two stations for the calibration and validation especially. The first one being the Berlin Road Station. This one is representative of more of the watershed side of things. And this is important because we want to ensure that the watershed inputs are correct when they're going from the watershed into the estuary system. And this station will be used to sort of check, is the watershed performing properly? The next station is the station at the estuary outlet. This one will mainly be the outputs from the estuary. And then really what's of interest is what happens between these two stations is sort of representative of changes that happen between the watershed and estuary and what sorts of processing is the estuary doing. So what sorts of reductions or increases in flow are we seeing? What sorts of reductions in nutrients and sediment are we seeing between these two stations? And that will help to capture sort of the benefits of the estuary in improving water quality and making sure that those are captured within the model. One of the really interesting, let me hit play on this. One of the interesting features about this watershed that is going to be a challenge incorporating into the Oldham Creek SWAT Plus model is the barrier break, because it is such a unique hydrologic event. And this is where the rains over the basin or the waves from Lake Erie cause such high flows, and this sand barrier that's between the estuary and Lake Erie breaks open. It causes pretty unique hydrologic response that is not very typical of watersheds, so it will be interesting to try to accurately capture this in the model or the simulations. Some of the improvements in SWAT Plus I'm just going to talk about briefly. So we've talked about the calibration and validation a bit. And these are usually just done at the outlet of a watershed. So we'll build our watershed model and then we'll look at the outputs just at the outlet. And we'll say, okay, our watershed model looks good. However, there's a lot of internal processes happening within the watershed that may be misrepresented, but still the overall summary of them looks pretty good. So with SWAT, when I talked previously about the landscape units, those are a new addition to SWAT Plus that help us more accurately, again, simulate different processes within the watershed, such as the upslope areas versus the riparian or inundated areas where things are more wet and there's different sorts of processing happening. So the benefits of this being able to have a more connected system represent things at a finer scale is that it will allow for much easier incorporation of the Oldham Creek estuary into the model. The improved connectivity and the ease for modelers to be able to connect objects will enhance the capabilities to incorporate this estuary. And one of the ways that the current approach that we're taking to represent the model into the estuary is sort of as a series of reservoirs. So the basics of this is representing the estuary as three separate reservoirs, each of them sort of mimicking the open water section, the section with cattails, and the section with floated vegetation, and then into Lake Erie. Representing the estuary as separate reservoirs will also give us more knobs to turn or more parameters to tweak so that we can ensure each of these buckets is sort of, or each of these reservoirs is capturing the heterogeneity of the reservoir or of the estuary, making sure that we're capturing the uniqueness of each of the sections, so different nutrient processing, different flow processing, what's happening there. Finally, once we incorporate the estuary and our model is calibrated, we can do climate and land use change analysis, which is sort of the end goal of having this tool. And just to talk pretty generally about an approach that I might take, we can use climate change scenarios, which are generated scenarios or global climate models that are generated by labs. We can take those, downscale them, format them so we can run them through the SWAT model. Then we'll want to generate land use and land management change scenarios of interest. From there, we can run both of these through the Old Woman Creek SWAT Plus model, and then look at the data, similar to how the previous project that I talked about, where we use SWAT, and we can assess vulnerabilities and potential adaptation plans. One of the really important pieces to this project is stakeholder advisory groups. So while I'm a watershed modeler, I am not an expert in Old Woman Creek, and it's really helpful to have people who are experts, who are working with people who are farmers, who have been doing conservation in this watershed to help advise with the really good local knowledge on what's happening in Old Woman Creek, how can we best represent the system. It's a really important piece to making sure that the watershed model is relevant to the end users and doesn't just sit and is not as relevant. So hopefully I can build this model into sort of a decision support tool that can be used to run land use and climate change scenarios in an easier format than once the project is complete. And this is one of the reasons I'm really excited to be a Margaret A. Davidson Fellow, is because a big focus of this research is ensuring that it's applicable to the watershed and that this will be useful to end users and that this tool will be used even once the project is done. So just to sort of wrap up the sort of adaptive management cycle and how watershed models fit into this, watershed models are just one piece of a larger puzzle in trying to figure out nutrient management and agricultural management and protecting our waterways, such as Old Woman Creek Estuary and Lake Erie. So we start with the edge of field studies, quantifying nutrients and sediment and discharge reductions through practices on the ground. We can use that data as well as in-stream data to build watershed models that help scale up that data to larger regions such as Old Woman Creek or even the Lake Erie Basin. From there, we can run scenarios on climate and land use change, see what sorts of impacts can we expect. If we were to increase any certain practices, would that help us in reaching our goals, water quality goals? And then finally, that can be developed into reports or things that people can eventually act on and enact in policies. The goal would be for the policies to then be transformed back into getting practices on the ground, and where people are implementing more practices, farmers are implementing more practices to reduce phosphorus, the phosphorus loading reduction. The phosphorus is reduced to Lake Erie would be the end goal. And this is a continuous cycle. We keep improving models with research, keep improving observed data sets on edge of field studies. Yeah. So I hope that you find you've maybe learned a little bit about how watershed models can be used to inform watershed and coastal management. I'd really like to thank, again, the Davidson Fellowship for allowing me to do this research with the Old Woman Creek NER. The Erie Conservation District, I've been working a lot with Bree, who's really helped me on some of that expert local knowledge. Old Woman Creek for really supporting me in this project and helping mentor me throughout it. And then my lab at Ohio State University for helping me as well. Thank you. I think that's all I have. Okay.
Thanks, Haley. That was really great. And looks like Aiden has another question. It said on slide 64, it looked like the model underestimated the peak flows. Ideas why, and do these lower estimates underestimate the impact of the higher actual flow on Old Woman Creek? So again, you can read it in the chat if that helps.
Thanks. Yeah, so this is just an example data set of what calibration and validation might look like. But yeah, that would be something to consider if it does underestimate the peak flows. There's also some corrections you can do once a model is finalized to sort of flatten out those biases even after the model is calibrated if it's not perfectly capturing the peak flows. But yeah, it is something to be mindful of. Yeah.
Thank you. Thanks, Aiden. Those are good questions. Does anybody else have any questions? Oh, go ahead, Haley.
Oh, and you're saying why does this happen? There's a lot of reasons that it could be underestimating peak flows, and those could need to be investigated, and then it could be fixed. It could be like certain management needs to be changed, or certain parameters need tweaked to more accurately represent the watershed. But yeah, there's a lot of different reasons why peak flows would be underestimated or overestimated, but a lot of those can be tweaked within the model to ensure that you have a pretty good fit.
Okay, great. Any other questions for Haley?
Hey Haley, Steve McMurray, really great presentation. I was kind of interested in the 3 different reservoirs that you chose. Can you maybe just speak a little bit more about the rationale for those 3 specific reservoirs, and what we know about the differences in nutrient processing between those 3? So the cattails, floating vegetation versus open water.
Yeah, so I think we are just hoping that, I'll go back to the slide. Oh, right here. We're hoping that we can capture some of the differences. I think there's not much evidence that there is huge differences. We just are like assuming at this moment. I'm working with a lot of like of the observed data to try to see how are we going to capture that. But yeah, I don't think there's extremely fine scale data that we're going to be able to compare to on the observed side. So we might have to use some theoretical assumptions on how nutrient processing would look differently in these different sections. But we want the model to be able to capture the variability that's seen, or some of the variability that's seen in real life, because the wetland is super variable depending on which section you're in. So
Yeah, absolutely. I guess another question, I don't have much experience with these types of models, but are you able to do any sort of like sensitivity or elasticity analysis?
sorry, you said sensitivity and what analysis?
And or elasticity?
Oh, I haven't heard of elasticity analysis, but
That might just be a population model thing. But
okay, yeah, we are able to do some sensitivity analysis, and I'll probably begin that soon in the calibration phase, where we're looking at what sorts of things is the model responding to and the model most sensitive to, especially in terms of parameters, or even we can test is like this model really sensitive to certain management being input into it. So yeah, that will be something that's going to be happening soon. Yeah.
awesome, thank you.
Yeah, thanks for your question.
Haley, we have another question. Can this model be used to predict the value to the farmer's land, as maybe they might need more motivation beyond the intrinsic value of Oldman Creek?
Yeah, so that would be, oh, sorry, I think there's some echo.
That's Emily. I'll get to Emily's in a second.
Oh, that's okay. Yeah, so that would be sort of, I wouldn't say that we can predict each farmer's field, or we can point to the HRU in the model and say that a farmer's field looks like this, but I can say we can definitely make some generalizations about farm fields in the watershed, and it will be interesting to work, I think, closely with Bree, who works a lot with farmers on conservation, on how we can best message this to make it relevant for everyone in the watershed. And there are benefits, like financial benefits, to some of these best management practices, which may be important to incorporate in like the final messaging of like what the model has to say. So not only will it improve Old Woman Creek, but if you do these practices on your farms, you can save this much amount of money in nutrients because they won't be leaving downstream. So yeah, that will be something that's definitely we need to consider, like as we move forward and like once the scenarios come out, how to message them.
Right. Yeah, I think that's an important point, is that, you know, the farmers don't want their nutrients running off. It is sometimes just what happens as rain, and they're trying to get the water off their land. So yeah, if they're having nutrient retention on their fields due to conservation practices, that will definitely be of a financial benefit or incentive. So Emily was mentioning that there is some recent research on nutrient retention thresholds for different types of wetlands, open water, stormwater, and natural estuaries, which mimic the 3 parameters of your 3 basins in your model. And then she linked the story map. Is this our story map, or is this a different one that people can check out, which is a graphic display of information, and a story map, and you can go through and get more information based on the different either pictures or graphs that are displayed. So it's a really nice visual way to display information. But I'm not exactly sure which story map that is, but I'm assuming it links back to the research she mentioned.
Yeah, sorry, this is Emily. That's the story map associated with the Science Collaborative Project. So that was the official outreach product associated with that research. So if you want to go ahead and click on that and explore, it'll provide you links to publications. And again, this is an emerging area, but it's nice to have this cohesive research within Old Woman Creek.
I really like that story map. It's really cool.
All right. Any other questions or comments for Haley? Haley did great. Thank you for sharing your research. We'll probably have you again next year as you're wrapping up your 2-year fellowship. So we do have, if no one has any more questions for Haley, we do have one other PhD candidate researcher on the call here. And if you've been to any of our other ones, you are familiar with any of our other brown bags, you're familiar with Carrie. Haley, can you stop presenting, and then I'm gonna show Carrie's slide, and Carrie, you can come off mute and let them know why you're here. Thanks, Haley.
Yeah, all right. I will wait for the slide to come up so that you can look at it while I'm talking. Yeah.
Can you see it?
Yes, I can. Hopefully everyone else can. My name is Carrie. I am a PhD student at BGSU, and I'm looking at I'm researching how environmental education events impact those people who attend them. So like attending this event and how that may change your opinions of the environment and what you're willing to do to protect it. So if you have about 10 minutes today and you're willing to take my survey, I would really appreciate it. There is a opportunity to enter in a drawing for an Amazon gift card too, maybe if you need a little incentive. On the screen, there's a QR code that you can scan with your phones, or there's a link underneath, and I'll paste the link in the chat too, so you can click on it and take the survey.
All right. All right, everyone. Thank you very much for attending. The next one will be October 1st, which is the first Friday and the first day of October. And we are going to be having a panel discussion about how we may be changing some of how we do our watershed report cards based on some research we've been doing across the entire western basin of Lake Erie. So look for that email towards the end of this month. And thank you all for joining, and we will see you soon. All right, good job, Haley. Your timing was perfect.
Thanks. I've never had to talk for that long. I was like getting real winded at the end.
No, you did really well. Your timing was perfect. You had a good pace of speech as well. And I think the big pictures, not a lot of text, and describing and isolating that information on the graphs, I think was really helpful to folks.
Yeah.
Oh, you're fine. Thank you for adding it.
Yeah, Haley, that was really well done. It's a lot. I mean, I'm new to this whole thing, but again, you explained it really nicely. And the fact that every plot came up and you explained it first, I taught a lot of students. That was a hard thing to get them to remember. So again, really excellent presentation throughout. Sorry for the questions.
Oh no, thank you. That
Yeah.
they were like, yeah, it gave me something to think about too. Thanks.
Yeah, there's actually I just moved from Iowa, and out there at Iowa State, there's a research project that's looking at plantings in the same field as the crop that would help with runoff even while the crop is there. But then, and then there's also work on that I saw, which was looking at where the runoff comes to put basically things that will filter out the nitrogen and whatnot. And anyway.
Yeah, that's interesting. I feel like Iowa also has a lot of really big agricultural research, but that is interesting about, I think it's called intercropping. I just saw a presentation the other day, and it's a popular thing in some country in Africa. I can't remember which one, but I didn't know that they were doing in Iowa too. That's really cool.
Yeah, one of my colleagues, they got about $10 million out of the I think I'm not sure which organization to do it. So it's
Yeah.
kind of interesting.
Yeah, that's super interesting.
Yeah, Iowa is the most modified landscape in the country.
Really? I didn't know that.
Yeah, it's all tiles, and like 90-some% of it's crop. And
Yeah.
anyway, just interesting. Okay, well, thank you very much.
Yeah,
and
thanks
Jennifer.
so much for coming and your engagement.
Thanks for joining us, Aiden.
Yeah.
Well, all right, Haley, I'm gonna stop recording.